Welcome to the Explainer. Today, we're opening up the Analyst's Playbook to master a truly fascinating topic, inferential analysis. Think of this explainer as your personal detective's guide to the statistical universe. You see, as researchers and analysts, we almost never get to look at the whole picture. Instead, we're handed a few clues, a limited sample of data. Our job? To use those finite clues to uncover massive, hidden truths about an entire population. It's a brilliant process of deduction, logic, and probability. And by the end of our time together today, you're going to know exactly how it's done.
Okay, let's dive into this. This quote right here from C.R. Cathari's foundational text on research methodology perfectly captures the ultimate goal of what we do. We aren't just collecting data for the sake of having a bunch of numbers in a spreadsheet. We're making a leap. We're attempting to move from the concrete, measurable sample that we hold right in our hands across this bridge of probability to draw a meaningful inference about the vast, unmeasurable universe out there. Honestly, it's the core magic trick of statistics.
To master this magic trick, we're going to follow a really simple 5-step roadmap. We'll start with inferential analysis explained, move on to estimating population parameters, unpack the logic of hypothesis testing, walk through the steps for testing hypotheses, and finally compare parametric versus non-parametric tests. By the end, you'll have a rock-solid framework for making statistical decisions. Let's kick things off with Section 1, Inferential Analysis Explained, moving from the sample to the population. Before we can start testing anything, we really need to draw a hard line between simply describing the data we have and actually inferring something brand new from it. Here's our working definition. Now, while descriptive analysis just profiles what's right in front of us, like the average age or the preferences of a specific group you just surveyed, inferential statistics is the engine that actually lets us generalize our findings to the broader world. It's strictly concerned with two major heavy-lifting tasks: estimating the values of unknown parameters of a population and testing statistical hypotheses to see if the conclusions we've drawn from our sample are actually valid.
Moving right along to Section 2, Estimating Population Parameters, Guessing the Unknown. This brings us perfectly to the very first major pillar of inferential statistics, which is estimation.
So I want to pose this question to you. How exactly do we estimate the unknown? If a researcher can literally never measure every single item in a massive population, how can they accurately guess a parameter that they can never be 100% certain of? Well, think about it like making a massive pot of soup. You don't need to drink the entire pot to know if it needs a little more salt, right? You just need one really good, well-stirred spoonful. As an analyst, you essentially have two ways to look at that spoonful. You can use a point estimate. That's a single, highly specific value used as your absolute best guess for the population parameter. It's incredibly precise, but because it's just one single number, it's also pretty risky. The chances of it being the exact true population value are pretty slim. Alternatively, you can use an interval estimate. This gives you a broader range of values, stated in terms of probability, that likely contains the true parameter. So a researcher basically has to choose between a precise but risky single number or a safer, broader range based on fundamental probabilities. All right, Section 3, the logic of hypothesis testing, from guessing to testing. Now we're transitioning to the second major pillar of inferential analysis. We're shifting our focus from simply estimating a hidden value to actively testing a scientific claim. So the crucial point is understanding this dichotomy. In statistics, we don't just set out to prove what we think is true. We actually set up what's called a null hypothesis, or H0. This is the default assumption, the status quo, that we are actively testing for possible rejection. We assume it's true to start, and we see if our data holds up. If our sample data strongly contradicts the null hypothesis, we reject it. And what do we accept in its place? The alternative hypothesis, or HA. That's our backup truth. It's a conclusion we accept when the default assumption completely fails the test of our data. And this brilliantly illustrates exactly how that plays out. Just picture a standard bell curve. That massive central area covering 95% of the curve, that's the acceptance region. If our sample mean lands anywhere in that big middle section, our null hypothesis survives. We accept that our default assumption is likely true. But take a look at those tiny little tails on the far left and right edges, representing just 5% of the total area. Those are the rejection regions. If our sample data is so extreme that it falls all the way out into those tiny margins, the null hypothesis goes there to die. The probability of getting that result by pure random chance is simply too low, so we have to reject H0.
Which brings us to Section 4, Steps for Testing Hypotheses, the decision-making flow. Now that we understand the logic of acceptance and rejection, how does a researcher actually perform this test in the real world, from start to finish?
Kothari provides a really great systematic flow diagram for this, breaking it down chronologically into 5 steps. Step 1, you clearly state your null and alternative hypotheses. Get them down on paper. Step 2, you specify your level of significance. Are you testing at a standard 5% risk level or maybe a much stricter 1% level? Step 3, you decide on the correct sampling distribution based on what kind of data you're dealing with. Step 4, you actually go out, take your random sample, and calculate the probability that a sample result would diverge as widely as it has, assuming the null hypothesis is actually true. And finally, step 5, you compare that calculated probability directly to your significance level. If it's smaller, boom, you reject the null. If it's larger, you accept it. It is a beautifully logical decision-making flow.
And here we are at Section 5, parametric versus non-parametric tests, choosing your weapon. We've reached the final fork in the road. You have your hypotheses all set, you know the procedure, but which specific mathematical tool are you going to use on your data?
Basically, there are 2 distinct families of statistical tests, parametric and non-parametric. And your choice here depends entirely on how much you can confidently assume about your parent population. Parametric tests are kind of the gold standard, but they assume your data comes from a normal distribution and they require precise interval or ratio data. But let's be real, sometimes you just can't make those strict assumptions. And that is exactly where non-parametric tests step in. They are what we call distribution-free, meaning they genuinely do not care about the shape of your population distribution, and they work perfectly fine with simpler nominal or ordinal data.
Now, if your data does manage to meet those strict conditions, you're going to use one of the standard parametric tests. The rules for choosing are actually pretty straightforward. You pull out the z-test when your sample size is nice and large, or if you happen to already know the population variance. You switch gears to the t-test for smaller sample sizes when that population variance is an unknown mystery. And the f-test? It has a very specific job. It's used strictly to compare the variances of 2 completely independent samples. These are incredibly powerful tests, but remember, they absolutely demand a normally distributed population.
Now, what's really interesting about this slide is the incredible flexibility that non-parametric tests offer us. When your measurements are a little bit messy or you seriously doubt your data looks anything like a perfect bell curve, these tests come to the rescue. Take the sign test, for example. It's literally one of the easiest tests out there because it doesn't even look at the numerical magnitude of your data, it just looks at the direction of the plus or minus signs of the observations. I mean, how cool is that? It allows you to reliably test your hypotheses without forcing your data into a strict mathematical box where it really doesn't belong.
So, there you have it. We've walked through the art of estimating the unknown, the core logic of the null hypothesis, and the mathematical tools you need to test it all. You've officially got the complete analyst's playbook in your hands. Whether you end up using a highly precise z-test or a super flexible sign test, you are no longer just staring at a random pile of numbers. I want to leave you with this provocative thought. What larger truth is hiding in your next sample? Because with the power of inferential analysis, you are now fully equipped to uncover the actual secrets of the universe from just a tiny piece of data. Thanks so much for joining me on The Explainer today, and keep questioning the data.